Welcome to a video lecture module covering Chapter 6 in Chawla and Meyers, Mechanical Behavior of Materials. Today, we'll cover geometry of deformation in crystalline materials, and also the theory of work hardening surrounding deformation. As a brief introduction, my name is Kevin Chu. I'm a fourth-year PhD student at Georgia Tech. I'm doing this as part of my teaching capstone with the Center for Teaching and Learning here, where we're provided with the opportunity to deliver lectures like this and improve our teaching style. I would appreciate any feedback you guys may have so that I may continue improving. This lecture can be split into two halves, the geometry of deformation and theories of work hardening. From the geometry of deformation section, you should be able to identify primary slip systems in standard crystal structures. Calculate the Schmid factor on a given slip system in any orientation. Determine the resolved shear stress from an applied load. Visualize the stereographic projection of the face-centered cubic structure, and use Diehls Rule to identify the active slip system for any load. In the work hardening theory, you should be able to explain microstructure changes during work hardening and the difference between single crystals and polycrystals. Then, you can estimate the temperature and strain rate effects on work hardening and metals and ceramics. Visually illustrate the difference between Taylor and Kuhlmann-Wilsdorf work hardening models. Then use these theoretical models to predict the strength of a material. Work hardening theory allows us to qualitatively describe what happens in the microstructure due to small-scale atomic deformation. But why do we care about these processes? Well, it turns out that the majority of processing methods of materials, for example metalworking methods, all involve large amounts of deformation. Thus, we need work hardening theory to describe the properties and structure of the resulting part. Forging, at the top left for example, presses a metal into a desired final shape through heavy dies. Rolling, on the top right, gradually reduces the thickness of material so that large, thin sheets can be produced. Aluminum foil, for example, is produced in this method. Extrusion, or wire drawing, pushes or pulls a material out of a small hole or small opening so that a long, thin material can be achieved. Stamping uses a thin sheet of material and is pressed between a punch and a lower die to create open volume parts, as shown here. I'll show a quick example video of forging using carbon steel for large automobile parts. A large molten piece of metal is placed into the die, and the upper die repeatedly presses it and deforms it into the desired shape. Modifications to the shape can also be affected by placing in punches such as this. You can see the large amount of deformation that's occurring in this material. If we skip ahead to the final part, you can see just how much force and how much deformation goes into shaping a metal part like this. And it's important to understand what happens at the atomic level when these parts are shaped. The shaping of these parts through forging is done through a process known as plastic deformation, or permanent deformation of the material. As we introduced in Chapter 5, this is carried by dislocations. An illustrative example of the atomic scale deformation and dislocation glide is shown here in a nanoindentation simulation. Here, the top surface of the material is pushed down, resulting in permanent plastic deformation. These defects you see propagating through the material are dislocations. Dislocations are the primary carrier of plastic deformation in metals. You can also see that they're gliding on parallel planes in the same direction. This is called a slip system. The slip systems can be described using Miller indices, and typically, slip occurs on close packed planes. If you recall, FCC close packed planes are 1-1-1 planes, for example. An important thing to note here also is that for the dislocation to move, the applied stress must have a component parallel to the dislocation Burger's vector to initiate slip. And we'll explore this with critical resolve shear stress in a few slides. This next slide shows slip systems in an FCC crystal. This looks complicated at first, but it's just important to remember that all these slip systems are symmetrical. They occur on 1-1-1 slip planes and 1-1-0 slip directions, for a total of 12 slip systems. The symmetry of these slip systems is perhaps more easily shown in a 3D model. Here I have a model of an FCC crystal here. You can see the face atoms and the full cubic structure here. The 1-1-0 directions are across the face diagonals, these atoms here as highlighted. Now, the 1-1-1 plane is simply the diagonal of this cube, and the slip plane is normal to this diagonal, which we can visualize here. The 1-1-0 directions are along the faces of the cube still, along this face, this face, this face. So for this single 1-1-1 plane, we have 3 possible dislocation Burger's vector directions. These make up 3 of the 12 slip systems. Another thing to note in FCC crystals is that 1-1-1 planes intersect along the face diagonals. For example, this 1-1-1 plane and the neighboring -1, -1-1 plane intersect along this bottom face diagonal. Dislocations moving along one slip direction can shift onto either one of these slip planes along the intersecting diagonal. This becomes important in later stages of work hardening, as we'll explore further on in this lecture. BCC crystals, on the other hand, have no close-packed 1-1-1 planes. Instead, they have a number of different slip systems that can become activated depending on the applied load. The slip systems are shown here, totaling 48 different combinations of slip planes and slip directions. This makes BCC crystals much more complicated to deal with. In the scope of this course, we'll focus on FCC crystals. HCP materials, on the other hand, only have 3 active slip systems. This makes dislocation slip more difficult, and other deformation mechanisms are more likely. To summarize, plastic deformation is primarily carried by dislocations moving on slip systems in metals. Slip systems consist of a slip plane and a slip direction. FCC has 12 of these slip systems on the 1-1-1 family of planes and 1-1-0 directions. BCC has 48 slip systems, but they are not close-packed. HCP has 3 close-packed planes along the basal plane. As I mentioned earlier, dislocations require the applied stress to be in the direction of the Burger's vector to initiate slip. What happens if the applied load does not align with the slip direction. We use Schmidt's law to calculate the portion of the applied load that is actually transferred to the slip system and slip direction. To do so, we simply calculate the angle between the applied load and the slip plane normal, and also the applied load and the slip direction. We multiply this by the applied load to find the shear stress that acts on the slip plane in the slip direction. As a brief exercise, predict which one of the orientations will give the highest Schmid factor. I've given you the angle of phi, the slip plane inclination. Consider also what lambda, the angle between the load and the slip direction, will be in both cases. The answer is that both of these orientations actually give a Schmid factor of 0. That means, with an applied load in either of these slip plane orientations, none of the load will be transferred to the actual dislocation. It turns out that the maximum load actually occurs at 45 degrees inclination of both the slip plane and the slip direction. This is simply due to the slip system geometry. As we rotate the slip plane, the angle lambda similarly changes, and thus we can actually only maximize half of the applied load. Once the internal resolved shear stress meets a certain threshold value, the dislocation begins to glide and the material deforms. This is called the critical resolved shear stress. It's a material property that depends on the temperature, strain rate, and type of material system. The key takeaway from this section is that even if an applied load is higher, if the slip system is not oriented favorably, the resolved shear stress, the true stress on the dislocation, may actually be lower. Once the critical resolved shear stress is reached and the dislocations begin to glide, they can glide out of the surface of the material. As dislocations continue gliding out of the material, this can eventually result in visible steps on the surface of the material, as seen at the right here in an aluminum-magnesium alloy. If the ends of the sample are constrained, as shown in the middle, internal rotation actually begins to occur. The internal rotation of slip planes means that the Schmid factor begins to change and multiple systems can now begin to become activated, resulting in further deformation of the material. To bring everything together, let's do the following exercise. An FCC crystal is loaded by 120 megapascals in the -1, 2, 1 orientation. Calculate the resolved shear stress for slip on the 111, 110 slip system. The critical resolved shear stress for this material is 25 megapascals. Please answer, will this material deform permanently? Take a few minutes, pause the video, and try to calculate this out. We can break this problem up into a few steps here. First, we must calculate the angle or the cosines between the slip plane and the loading direction and the slip direction and the loading direction. This is simply the dot product over the magnitudes of these vectors. The Schmid factor is the product of these two cosines, and we calculate this out to be 0.136. The next step is to resolve the shear stress from the applied stress. The applied stress was 120 megapascals. And with our Schmid factor calculated from step 1, this results in a resolved shear stress of only 16.33 megapascals. To determine if the material permanently deforms, we compare it to the critical resolved shear stress. As you can see, the resolved shear stress is below the critical resolved shear stress of 25 megapascals. Thus, the dislocation on this slip system will not move, and the deformation will not be permanent. It's important to note that we've only calculated Schmid factor on one single slip system. Other slip systems in this material may still be active due to a higher Schmid factor. How can we determine then which slip systems are actually active under an applied load? We can use a brute force method. We can calculate the angles and the Schmid factors for every single slip system in the FCC crystal. This is 12 different calculations that we must do to determine the maximum Schmid factor. Another elegant method is the use of stereographic projection, and we can use this to determine the active slip system graphically. Stereographic projections are a method of representing the three-dimensional angular relationships between planes and directions on a 2D graphical plane. This also looks complicated at first, but you can think of it as a light source shining through a crystal and observing the angles of reflections of all the plane normals. To generate this stereographic projection, we can first start by imagining a crystal inside of a sphere. From one of the slip planes in this crystal, we can draw the plane normal and extend it out to the point it intersects the sphere surface. If we use the green plane as a reference plane, we can also draw a line intersecting to the bottom of this sphere down here. From these 2 points, we can draw connecting lines between the intersecting points on the hemisphere. The point that it intersects the reference plane, the green circle, is called a pole. The position of this pole preserves the angular relationship between the original plane and the reference plane. If we repeat this process for all the slip planes in a system, we end up with this extremely complicated stereographic projection, but one that preserves all the directions and angles. A simpler version for only FCC can be shown here, showing the 111 and the 110 family of directions and planes. We can use this to predict the active slip systems under an applied load. The procedure for doing this is known as Diehls Rule. First, we determine the location of the tensile axis by summing the pole indices. For example, if you have a tensile axis along 1, 2, 3, we find the triangle of the stereographic projection in which this axis lies. We can do this by summing the 001, 011, and the 111 to give us 1, 2, 3. This places the active triangle in this quadrant of the stereographic projection, and the triangle can be identified in this way. Step 2 is to determine the slip plane by finding the 111 family's plane in the active triangle and reflecting it across the opposite edge of the triangle, shown in green here. Reflecting this gives us the slip plane, -1, 1, 1 in this case. The third step is to do a similar method and determine the slip direction. We find the pole of 110 type, shown here in blue, and reflect it again across the opposite edge of this triangle we found earlier. This gives a slip direction of 101. We've now determined both the slip plane and the slip direction given an applied load in the 1, 2, 3. Recall from earlier that the crystal will rotate internally during loading if the ends are constrained. To determine which direction of rotation, we observe the original tensile axis moving towards the slip direction that we've determined previously, circled here in blue. Zooming in on these two triangles from the stereographic projection, the tensile axis 1, 2, 3 will move towards the 101, until it hits the boundary of these two triangles. Once it reaches the boundary of these two triangles, in this case, the 1, 1, 1, two slip systems are now active on the stereographic projection. This animation will show this internal rotation and also recap Diehls Rule. You can see with the constrained ends, the internal planes of the material begin to rotate. With Diehls Rule, we first identify the active slip system using the method previously. We sum the corners of the triangle to determine if the tensile axis is the sum. Then we determine the reflection plane for the slip plane, the 1, 1, 1. Reflecting across gives us the 1 bar 1, 1 slip plane. We do the same for the slip direction again. And reflecting across here gives us the 1, 0, 1. Once we've determined the slip system, we can determine the direction of rotation of the crystal. The pole, again, will move towards the slip direction 1, 0, 1. Once the pole has fully rotated into the boundary between these two quadrants, two slip systems, this quadrant and this quadrant, are now equivalent, and slip is activated in both. Conceptually, these two slip systems now have the exact same Schmid factor. The links to these animations will be below in the description for you to explore on your own, and I encourage you to do so. To summarize, in this module we've covered the concept of slip systems. Dislocations move on slip systems, which are a combination of a slip plane and a slip direction. An external applied load results in a resolved shear stress on the internal slip systems. Different slip systems in the same orientation may have different Schmid factors. And to determine which one is active, we use Diehls Rule on the stereographic projection to determine the active slip system and the direction of rotation. This concludes the first half of Chapter 6, Mechanical Behavior of Materials. We've covered the geometry of deformation in this module. If you have any remaining questions, please speak to Dr. Singh or email me at the email shown here. If you have any feedback for the lecture delivery or content, please also send Dr. Singh an email so that I may continue improving my teaching.